To the ancient eye, without the use of spyglass, only 7 of these wanderers, or planets as they were known, could be seen among the thousands of lights that bejeweled the firmament. The wanderers were different.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts in England and Sweden, Matthew Russell and Linn Boldt-Christmas.
Oh yeah, baby. Christian Huygens. That was Christian Huygens talking about the planets. Welcome back to the show, Linn. How are you?
Hello, I'm lovely, thank you. How are you?
Yeah, I'm pretty good. Yeah, very, very busy at the moment. Kind of, once I get through this week, I'll be back to being sort of almost human, but I've got a ridiculously hard week ahead of me.
Well, I feel like I've been saying that every week for the past 20 years. It's like, if I can just get through this week, everything will be fine cruising. And then you start planning, you sort of, as everything comes up, you're like, oh, I have to do this thing. Okay, well, I'll do it this next week, because then that week is empty. And then by the time that week rolls around, it's not empty anymore.
Yeah, it's busy, isn't it? But at least we're coming up to Christmas time.
Exactly, which of course is super relaxing and not at all stressful, with zero travel or family obligations. So a very relaxing time indeed. Yeah,
exactly, absolutely. So today, Linn, I thought we were going to talk about, we'd have a little chat about Mercury and Bepi Colombo.
Yes.
Because the last of my little snippets from the ESA Open Day is with Elsa Montagnon, who is the Bepi Colombo spacecraft operations manager. Do you know her? Have you ever met Elsa?
I do know the name. I haven't met her personally. I actually have a, I don't really know how to bring this up, but actually Bepi Colombo and I have some painful memories together.
Oh no!
And I'm gonna be vulnerable here. I appreciate some respect in this difficult time while I recount the story. I was actually supposed to be at the Bepi Colombo launch in 2018, but my research project at the time meant that I could not, because our supercomputers were misbehaving. So I had to go to England instead of French Guiana. And then when I got to England, there were loads of power cuts and the supercomputers didn't work anyway. So it was all for nothing. And I could have been at the launch, but I wasn't. So it's okay. It's not like I'll regret that for the rest of my life or anything.
Oh no, that's an absolute nightmare.
I know.
That's a nightmare. Well, the good thing is I've actually got two little snippets of Elsa Montagnon, because I went to Esoc and saw their. Oh yes. There's a little model at Esoc that's like where they run all the computers and stuff, and so I've got a little snippet of her explaining that when I was at Esoc in Darmstadt. And also, obviously, from ESA Open Day. Of course. Yeah, I love Bepi Colombo because I was actually in French Guiana and saw it being prepared for the launch that you missed.
Really? Gee, wow, cool. Okay, yeah. You know what? Joking aside, I do love Bepi Colombo. I'm, clenched fist aside, it's actually a really, really amazing mission. I have nothing but exciting things to say about it.
Let's talk about Mercury first, just so we can set the scene for where poor old Bepi Colombo has to get to.
Yeah, it's not a very nice scene, actually, I guess.
No, it's not. It's not the best of scenes, is it? The old Mercury.
Matt, what's your favorite planet? Yeah, and why is it Mercury?
Why is it Mercury? Because it's named after the lead singer of Queen. My favorite band.
Yeah, exactly. It was called something else, something stupid that no one even remembers. And then after that, they were like, guys, we have a new name.
After the Live Aid performance, they renamed it Mercury. Yeah. I can't even remember what it was called before that.
I think it was called Quicksilver or something.
Yeah, something like that. Yeah. No, it was called the Jumping Planet, I believe.
Yeah,
exactly. The Assyrians called it the Jumping Planet, or Naboo, I believe.
Oh, yeah.
There we go. Yeah, that's what it was called.
Beautiful.
Of course, Hermes as well. The Greeks called it Hermes.
Oh, yes, the postal service.
Or, isn't Hermes the name of the spacecraft in one of those films about going to Mars? In fact, hang on a second. It was wasn't it the name of the original space shuttle?
No, it was. No, it was the CNES, the European one. It was supposed to be. Yes. Yeah. It was supposed to be in the 70s. It was going to be, superficially similar to the space shuttle. I like to imagine that alternative timeline where that actually happened, and we had a beautiful ESA space shuttle.
Yeah, well, maybe you could write that alternate timeline for the next season of For All Mankind.
Yes, and then we'll start a spin-off podcast where we go through the space fic, the fanfic.
Tell me an interesting fact about Mercury. Hit me with your favorite Mercury fact. Now we've established that. Is Mercury your favorite planet then?
Okay, well, I'm so glad you asked. I actually, the other day, I was trying to think of what my favorite planets are. And I mean, it's a little bit like asking which child do you love the most. Of course, you tell the children, I love you all equally, but maybe there's one that's a little bit better. And I mean, I think at least Mercury is in like my top 4, which is actually not very flattering when there's not that many.
There's only 7.
Yeah. Well, I don't know. I mean, okay, so in my work, I like rocky terrestrial planets. And I mean, the competitors are Venus and Mars. I would actually argue that maybe Mars is overrated. Gasp. I know. I might get cancelled now, but
I agree.
I mean,
compared to Venus, how exciting is Venus?
Venus is like, it's hard to beat Venus realistically. So I would say Mercury is maybe my second favorite planet.
On average, what planet is closest to the Earth?
Well, you would think either Venus or Mars, right? Because they're the ones that are next to Earth at all times. But what's the answer?
It is indeed Mercury.
What?
Because it's the closest to all the planets because its orbit is only 88 days. So it's always kind of a lot of the time it's on the same side as the planet that you're measuring it to. So yeah,
of course, yeah. Because I mean, I guess if you're picturing the solar system, if Venus and Mars can both be on the other side of the sun at some point, which means that it's very far from the Earth.
Now here's the other one that I think is like even surprised everyone. Most people thought that Mercury is going to be tidally locked. Now you can explain tidally locked, Linn. I know you can.
Tidally locking is something that happens very often when you have planets that are close to their host star, where they are basically orbiting in such a fashion that they have one side of the planet that's permanently facing towards the star and one that's permanently away from it. So you would have a permanent day side and a permanent night side. You know, on Earth, we have days and nights and we're spinning around and, that we have, but depending on where you are at what time of the year, we have roughly the same amount of day and night at any one point on Earth. But for many planets that are closer to the host stars, and we see this a lot in exoplanets, you have this one side of the planet that is constantly facing the sun or its sun, and one side that's constantly facing away. Kind of like the moon, which is tidally locked to Earth. We have this one face of the moon that we see all the time.
Yeah, and presumably that's because they're close to their sort of parent orbiting body, right?
Exactly.
And it's just to do with the energies and things like that involved in sort of slowing it down. But
exactly.
So everyone just assumed that for a long time with Mercury, just thought, because Mercury's orbit is about 88 days or something like that, and they just assumed that the day itself would last about 88 days as well. So obviously it's tidally locked. It would rotate one rotation for every orbit of the sun. However, they measured it from Arecibo Observatory, with RIP, poor old Arecibo, and realized that, in fact, using radar, they actually realized that the planet's rotational period was 59 days. So that's only very, very recently that they sort of figured that out. And do you know?
Yeah, wow.
Do you know who noticed the mathematical coincidence, he thought, perhaps, between 59 days and 88 days? Do you know who noticed that was that 59 is 2/3 of 88? Do you know who spotted that?
No, I don't. Please tell me.
it was none other than Giuseppe Bepi Colombo.
Mr. Bepi!
Yeah. So that's one of the reasons why Bepi Colombo is called Bepi Colombo, after the great Italian astronomer Giuseppe Colombo, who noticed this weird 3-2 resonance orbit that Mercury has around the sun.
That's amazing.
Yeah, how cool is that? Now, I have no idea why it does a 3-2 resonance. Do you? Like any, but I think Giuseppe Colombo actually explained it, but I don't know anything about it.
No, I don't actually know that. I mean, we do see a lot of these weird resonances in the universe, or well, in our solar system, quite a lot. But I'm not sure actually why exactly that number comes out of Mercury and the Sun.
Yeah, it's weird, isn't it? I mean, yeah, you see it a lot in Saturn's ring systems, don't you? All those weird
exactly
sort of ratios of resonances.
Yeah, and we found a couple of exoplanet systems where you have some funky resonances that come out between the different planets and their host star.
Now, the other thing that Giuseppe Colombo was pretty hot on was his ability to work out things like the fact that to get to Mercury, you were going to need to have a gravity assist.
Of course, yeah. The gravity assist, I think it was used for the first time for going to Mercury.
I think the Russians used it on something like Luna 10 or something like that. But I think you're right, and certainly interplanetary wise, in terms of planet to planet, yeah, I think Mariner 10 was the first to go. Yeah. Was the first to use that, a gravity assist from another planet to get to another planet.
Yeah, I think if I remember correctly, it takes more energy to escape the solar system, actually, than it takes to reach Mercury. Because the problem is that when you're so close to the sun, to actually go towards Mercury but not end up at the sun, you need to do some pretty heavy braking, if you can imagine that. I mean, imagine you're wearing roller skates and you're going towards into like a big bowl, and the sun is basically the bowl in the bottom. But instead of actually ending up at the bottom, you want to catch another skater who is nearer to it. You'd have to actually sort of catch up with them in a weird way, and yet also avoid the big sort of apex in the middle or in the bottom.
Yeah.
So it's actually pretty tricky to reach Mercury. You'd think, it's not that far, but it's actually much more challenging than that.
Did you misspeak? Do you actually mean it's more energy to get to Mercury than it is to leave the solar system?
Sorry, yes.
Yeah, because it's just you've got this huge change of velocity, haven't you? You've got to somehow get in and then sort of slow down in time to get in orbit around Mercury. So do you know how Bepi Colombo, the spacecraft, does it?
I imagine you're going to tell me.
well, I kind of can. I can't remember the exact details, but Elsa does go into it. So it does a whole crazy amount of going past all the different planets. So it's already done It's done one round Earth, a gravity assist, came back to Earth, and then after going round the sun, comes back to Earth, does a gravity assist, and to slow itself down rather than to speed itself up like the Voyagers did. And I always think the greatest thing about that is every time... So when Bepi Colombo came back round Earth to slow itself down, it has fractionally sped up Earth in its orbit. So our days are ever so slightly... Sorry, our years are now ever so slightly shorter thanks to Bepi Colombo. Can you believe that?
Gee, thanks, Bepi.
Thanks a lot.
Yeah.
Which means I'm aging slightly faster than I need to. Yeah. How annoying
I'm
is
gonna
that?
Be 85. I'm going to be 85 and be like, it's not really my fault. Do you know what I love is that because I have this mug, right? There's a wonderful mug that I'm sure is probably still on sale somewhere this ESA mug of the BepiColombo, and it has all the dates of the flybys, where, you know, it says like the 20th of June or whatever, and the year with the sort of checklist of all these flybys. And I'm now kind of halfway through my mug. And so looking at it and seeing that, you know, I think 2025 is the last date, and it started in 2018. So I'm going to feel emotional in 2025 when I look at this stupid mug and be like, wow.
You've had it for the whole time.
Years.
Yeah, so
yeah, I got it just before the launch.
So it's done it, yeah, so launched in 2018, did a flyby Earth in 2020.
Earth flyby, yeah.
And then it's done a couple of Venus flybys now.
2 Venuses, yeah. And what I love that the timing of this was so amazing that this famous Phosphine paper that came out in September 2020, where some astronomers published that they think that they had found detections of this gas, phosphine, in Venus's atmosphere. And it was a pretty controversial claim. And then I think it was September that this came out. And then all these ESA scientists were like, well, we're going to be in the neighborhood on the 15th. We can check it out if you want. And because it happened to be doing this Venus flyby just less than a month after, they were like, yeah, we'll turn on our instruments. We weren't gonna, but we will. And so now they actually did this attempted detection when they flew by in October 2020. I haven't actually read if there's any data that's come out yet from that, but I just love that timing.
Yeah,
it's such a great thing with scientists when they get to do that.
It was awesome because I actually emailed ESA to find out if they were going to switch on their instruments, and I got an email straight back saying, "Oh yes, we are, and we'll let you know what's happening." But they said that,
I bet.
Which they haven't, but that's only out of my laziness for not following up.
Yeah.
But I believe that second more recent one, which was actually pretty much only a couple of days before we spoke to Elsa in this interview that's coming up.
Oh right.
I think that second flyby was a lot nearer, so it should actually have better data anyway.
Yeah,
but I think that phosphine thing has definitely kind of slowed down a little bit, hasn't it?
I think so. And I mean, we're now in December 2021, and I think it was October 1st, 2021, they had the first Mercury flyby. And did you know that occurred on what would have been the 101st birthday of Bepi Colombo? The human, not the mission.
I was
How
going to
great
say,
is that timing?
it's a very old spacecraft. No, that is insane. That's insane. Presumably, that's a coincidence and not him being incredibly good at.
Yeah. I wonder. I bet you any money that they sort of did the sort of tentative schedule, and they realized it was going to be on 2nd of October or someone, and then someone was like, "Guys, what if we launch a day earlier?" Exactly.
Well, I suppose there's a 1 in 365
65, yeah,
chance,
exactly,
or something like that. You know, they should have launched a year earlier, and then it could have been on his 100th birthday. Did you say 101?
They missed the trick there. 101, yeah.
Oh man! Now
close but no cigar.
So even with all those gravity assists, and this is something that Elsa mentions, is that they have to use. They have to use lots of different forms of propulsion to actually make this thing work. So they have ion.
Really?
Yeah. So they've got normal rockets, like liquid fueled rockets, but on board for the really heavy duty stuff. But they've also got ion thrusters as well, which is, I believe, the first time they've used ion thrusters in the inner solar system.
Wow.
So there's 4 solar electric ion thrusters, and I've stood next to the solar panels of Bepi Colombo, and they are massive to power these things as well. So yeah, at least there's plenty of sunlight near Mercury. Yeah, it's not like, but that's probably a problem in terms of like the solar panels that you can use and how you have to have them so they don't overheat and all those kind of things. Yeah. There's that one. There's because Bepi Colombo, I'm sure that Elsa will talk about it. You know, it has these different components, different modules. And if I remember correctly, there's at least one of them has this cool feature where, in order to keep itself cool when it's, you know, being blasted by the sun that's basically what feels like a few centimeters away from the sun, and it actually spins around very fast to keep cool, like a little ballerina. Yeah, spinning. It's a spinner, isn't it? So
exactly.
It's also got another very cool feature, and there's some pictures of it with the there's some pictures of it with the model that they used for to help with the design. They look like Venetian blinds. They're these fins that actually cover the radiators, but they look exactly like really crappy office blinds. But they're not, because there's a test model for BepiColombo. In fact, Elsa mentions this as well. It's actually in the Science Museum in London if you want to go and see.
Oh, really?
It. But it's missing those fins, because those fins are the actual ones that went off on the actual flight model. So they're obviously quite expensive, however they're designed.
Hopefully they won't do that thing that office blinds do, where they immediately start sort of one goes one way, one goes 45 degrees. I assume they're a little bit better.
Yeah, the worst thing is is the actual stick bit where you can use it to sort of make the blinds less see-through or more see-through.
Oh my God, yeah.
And that bit always breaks at the top. And why do they make them so feeble? Why do they make them so feeble? So annoying.
This is the
blinds.
Deep state Venetian blind industry. They've got their fingers in many pies. Wake up, sheeple.
Was Giuseppe Colombo a Venetian? Do you think?
Oh my God, this goes deeper than any of us could have ever thought.
And did he go blind looking into the telescope at Venus because it's so close to the sun? I
gotta go. I have some calls to make.
Maybe that's it. Maybe the Venetian blinds are named after Giuseppe Colombo. No,
I think this is it.
Here's an interesting fact about Mercury. It's one of the only planets that Hubble can't look at because it's too close to the sun. It's too close to the sun, so they daren't use the Hubble on Mercury because my eyes. I am blinded.
It is hard to observe Mercury. I mean, this is a little bit why I like it so much. I feel like maybe the sheen has rubbed off from Mars on me, because I mean, okay, fine, I love Mars. I'm not gonna lie, but I'm saying that Mars now we've been so thorough in trying to study it in the last few decades. Venus is mysterious because we can't really we haven't really been able to see what's on the surface before. And then Mercury as well. I mean, both of these are very poorly studied, actually, for different reasons. So I think this is maybe why I like Mercury so much. I'm like, what are you? Who is she?
Yeah. Well, Bepi Colombo should answer quite a lot of questions.
Yes,
lots and lots of
absolutely.
Lots and lots of questions, because there's quite a lot of water ice on Mercury as well, they reckon. Considering how ludicrous that sounds, there's quite a lot. Guess how many countries have been involved in the mission? Do you think?
Oh, wow. Well, it's ESA and JAXA, right?
Mm-hmm.
So Japan plus the ESA member states?
Yeah, roughly 16.
That's my cop-out.
It is a bit of a cop-out. 16 different countries. 1,000.
Wow, that's amazing.
1,200 engineers have worked on the mission, and am I allowed to mention the University of Helsinki, or is that?
Oh, that's okay. No, we just hate Denmark here in Sweden.
Oh, okay. So you're
Finland's
all right
great.
You're right with the Finnish. Okay.
Denmark. Yeah.
So yes, so the University of Helsinki, and some British universities as well, the University of Leicester and the University of Aberystwyth, helped design two of the instruments, MIX and SIX, the Mercury Imaging X-ray Spectrometer and the Solar Intensity X-ray Spectrometer. And MIX and SIX are Finnish for why, ? And SIX is Finnish for that's why, !
Oh, I love that. That's amazing.
Yes. So MIX and SIX are the two instruments that
Mix
University of have a MIX and SIX from the University of Helsinki, and with a little help from some British universities as well.
That's incredible.
And the Brits actually built the electric propulsion, kinetic. Yeah. So totally international effort. Now, the one thing that I loved, by the way, when I know, did you You've been to French Guiana, haven't you?
I haven't.
What? Oh no!
Oh no! Come on, Matt. I just opened my heart up less than 20 minutes ago, and you just pried open a bucket of salt. And was like, oh, you've been to French Guiana, haven't you? Oh no, that's right. Your dreams were crushed.
Oh
jeez.
No!
Yeah.
Ow,
so
ouch.
no, I have not been to French Guiana, Matt. Thank you.
So one of the things that I saw, I was looking through the window into the room while they were fueling Bepi Colombo up. They're literally there.
That sounds like you also were not welcome there, actually, if you were looking through the window. That makes sense. I'm now picturing you like in the bushes.
I definitely
spiders in your hair.
I definitely wasn't allowed in that room, put it like
Okay.
Yeah, in fact,
that's fair enough.
we all had our cameras taken off us to check that we hadn't taken pictures of certain things. It was very interesting. But there I was looking through the window with Eric Berger at these people stitching the blankets, hand stitching these thermal space blankets that go over the actual Bepi Colombo itself. You know, to control.
They should have got a little group of nanas all knitting blankets together.
Well, I have to say, I think they were actually all women. Weirdly, it has to be coincidence, but it was quite amazing. They were there, like just hand stitching these blankets. 97 layers of aluminium, plastic, and glass ceramics.
I can't imagine it.
So that these are, they keep the whole thing at kind of room temperature as much as possible, because computers don't like going from ridiculous temperature to ridiculous temperature.
Yeah, I mean, I don't either, but they really
400 degrees C on the sun side, so that's like twice a pizza oven, to minus 190 degrees centigrade on the night side, which is pretty much Helsinki in the winter, right?
Yeah, Christmas in Sweden. It's
Christmas in Sweden.
Basically that now.
So there you go. So it's that's the design challenge, I would imagine, isn't it? With Bepi Colombo is getting that whole thing so it actually works.
Well, that's the thing, and I mean, it's something that hasn't really this proximity to the sun has really not been an issue with other planets that we've explored, other bodies. So it's really quite a unique challenge.
It's absolutely crazy. Now, what do you think's hotter, the surface of Mercury or the surface of Venus?
That's you shouldn't ask me that because I know the answer. So I'm going to say, oh, I don't know which one is hotter.
Oh, come
please.
on! No, I knew you knew the answer. Yeah, Venus is hotter. Yeah, it's only gets to 427 degrees C in the day.
Yeah, quote only.
Yeah.
Only, come on.
It only gets to that.
Yeah.
Now, which has the smallest axial tilt out of Venus and Mercury, or Mercury and any planet?
I'm not sure actually about axial tilts. I think Mercury doesn't have a very big axial tilt though, right?
In fact, yeah, you're correct. It has the smallest at only 1/30th of a degree.
I'm getting nervous now. I feel like I'm on Jeopardy.
You are a little bit, but you did well. You've done well with. You're 2 out of 2.
Haven't used any lifeline. Yeah.
You got 2 out of 2.
My lifelines.
Now, I want a true or false on this one.
Okay.
Wait,
hold on.
Out of all the planets, does Mercury have the most eccentric orbit?
I know it does have. I'm going to say true.
That is true because Pluto is no longer a planet. But I think Pluto would have won. But yeah, you're correct. Only because Pluto. Yeah, it's perihelion. It's only 66% the distance of aphelion. Whereas Earth, so it's massively eccentric.
That is significant.
Yeah, Earth is 97%, and that's that changes by millions of miles. But yeah, Mercury's is insane.
Yeah. Earth is 97%, and we're like, it's absolutely not circular at all. Don't be insane. So yeah, no, this is significant.
Yeah, so it's properly pine nut shaped its orbit rather than a sombrero.
Yeah. toasted pine nuts in this case.
It is toasted pine nuts, yeah. Because I do think that because with the Earth, obviously, the distance to the sun makes no difference really to the temperature here on Earth. It's much more to do with our axial tilt. But
Mercury having such a small one.
Yeah, exactly. That definitely experiences seasons based on its distance from the sun rather than its axial tilt. Although probably the seasons doesn't really have them because it's just intensely hot on one side. Oh, actually, I suppose it must be weird, mustn't it? Because the planet must go through vast times of being very, very hot and slowly turning into night. And I mean slowly. You can walk around the planet.
Oh, yeah. Okay, yeah. So if you want a slow, romantic sunset stroll, I would not recommend Mercury. No, I was distracted because I was trying to think Mercury's atmosphere because it is very thin. So this is also quite an impact on, if you think about weather and temperature on planets, then atmospheres are very, very crucial in how they sort of distribute the heat. Because you can have a tidally locked planet where you have all the sort of sunlight coming on one side, but then you can have these dynamic processes in an atmosphere which would then sort of distribute the heat so you can still have, more evenly distributed, let's say, heat across the planet. But Mercury doesn't even have that going for it. The thing that's blowing my mind is that we've found so much water that it's seemingly so abundant in the universe.
Oh, yeah.
Like that, if that's something that, if 40 years ago, I think people would have been impressed by.
And now here's something I really didn't know, and that is, what do you think that Mercury has a magnetic field? Like Earth has a magnetosphere.
I happen to know that, yes, Mercury does have a fairly significant magnetic field.
It's not just fairly significant; it's actually bigger than Earth's.
Yeah.
Which is pretty cool, isn't it? So it must have loads of,
which is incredibly
molten
cool.
metal like sloshing around inside the core.
If anyone is playing bingo back home, how many times has Linn mentioned exoplanets on a podcast that's not about exoplanets? Here's like number 5, I think. The thing about exoplanets is that you have so many of them that are closer to their parent stars. And so magnetic fields and planets and how they interact is actually a really interesting and important topic. And so figuring out how magnetic fields happen in stars is already kind of a question mark, but we're working on that. But then on top of that, figuring out how magnetic fields are generated in planets is an even bigger challenge because, as I've said before, stars are all basically the same thing. You have bigger ones and smaller ones, and then you have, different characteristics that arise from whatever their initial mass was. But overall, we kind of know the life cycle. Like we know, okay, this star has, one solar mass. That means it's this type of star, and that means it should roughly follow this life cycle. But the thing about planets is that they are all so unique, and they are much, much more diverse in their composition and their life cycles and all crazy things like that. So figuring out how magnetic fields arise in stars, the fact that that's already a challenge, and we already have so many more stars to compare to each other to sort of triangulate an answer for things like that. And the fact that we don't know that 100%, to then say, well, what causes magnetic fields in planets, that's an even bigger question. What are magnets anyway?
Wow. That's one of my favorite ever Feynman clips, is him explaining to someone how he can't explain what magnets are to him.
Yeah, don't ask your local scientist what's a magnet. They'll get sad.
He almost
they get insecure.
Almost gets in a bit of a mood with the bloke that asks him a question. That's the funny.
Yeah.
Now, my favorite thing about Mercury is it was one of the very first clues that Newton was wrong.
I love that. Expand, please.
Well, as Mercury goes round the sun, its actual rotation, particularly the slow rotation at perihelion, can't quite be explained by Newtonian mechanics, even if you take into account all the perturbations of the other known planets. So as you look at it, it's like there's something else going on here that's not quite right. So its orbit's not quite what you'd expect if you just used Newton's laws of motion. And this was something that was known by a guy called Urban Le Verrier, who analysed the transits, observations of the transit of Mercury between 1697 and 1848, and showed that there was something wrong, that the prediction was wrong. So there was something wrong, and it took Albert Einstein's general theory of relativity to show that Mercury is moving so damn fast that actually you have to take into consideration relativity. It's actually there is a
That's amazing.
So it was one of the things that everyone was going, this is a big mystery. That is one of the things that everyone went, oh God, this Albert Einstein paper kind of explains that. How cool is this? So
this Einstein guy, I think he might be onto something. He seems pretty smart.
So I think Mercury played a sort of huge role in that, which is it's one of my favorite things. So maybe Mercury is my favorite planet. I don't know.
There you go, ladies and gentlemen.
Yeah, it's.
You heard it here first.
And it might not even be the planet it once was. It might be a planet that got smashed to bits, just leaving the core of a planet behind. Although I think that evidence is getting weaker and weaker. That it's actually the core of an old planet. But you'll be able to tell me more about that.
I seem to recall that. Well, I seem to recall that one of the motivations for BepiColombo, like obviously there are a number of things we want to investigate, but one of them is to do with formation history, let's say, because. Okay, well, now we're on to number 6. Another thing about exoplanets, because, like I said, that they are so often close to their host star, investigating how nearby planets form near their host stars. That's another important piece of the puzzle as well, because Mercury is more at a kind of distance from its host star that we see often. I have to confess that when I picture BepiColombo, I do not picture it how it looks. I picture the little cartoon ones, from the Esoc cartoons. Like that's all I see in my head. Same with Rosetta.
I think ESA do a pretty good job with their little cartoons. We should mention, of course, BepiColombo is yes, European and Japanese, which I think in itself is pretty unique, having a spacecraft that's carrying two spacecraft, a stack of spacecraft, basically.
Yeah. I think we're entering a really exciting time in planetary science history, because there are so many. There's kind of like this rejuvenation for solar system exploration. There's so many fun, exciting solar system missions on the horizon, and BepiColombo is definitely one of my favorites. But we've also got JUICE coming up. We've got all this talk about new Venus missions and all this stuff. So I think the 2030s are going to be pretty exciting.
Yeah, no, absolutely. I think there will be a renaissance. I mean, I think it's actually a little bit embarrassing how little we know about Venus and Mercury, really, considering how much we know about some exoplanets. And we're seeing black holes collide and all those kind of things. Yet we don't really know much about Venus and Mercury. It's just crazy, isn't it? So exactly. Solar system missions, I think we should definitely have more of them, and there's more of them in the pipeline, which is super exciting, isn't it?
Yes.
Shall we have a quick listen to my couple of interviews? I think I might just roll them in order of
I would love to.
So, bishti bashti bosh, écoutez.
The Interplanetary Podcast, putting the ace back into space.
Elsa Montagnon, the mission manager, recently appointed mission manager for BepiColombo, is joining us here on ESA Open Day, on the virtual stage, on the virtual day. Welcome, Elsa.
Hello.
Good to see you.
Hello, Elsa.
Good to see you.
Elsa, well, you are working as a mission manager for BepiColombo. I think the first question I have for you is sort of the elephant in the room, and then we can go into more details of the mission. But something very important happened yesterday, the sort of breaking news in a way. So maybe you can tell us a little bit about that first.
Yes, 2 days ago we had our 2 days ago or yesterday, depending on the time zone you're sitting in, we had our first flyby of Mercury. So BepiColombo is a European and Japanese mission to planet Mercury. We've been working decades on this program, and basically on the 1st of October UTC time, we made our first encounter with our target planet, and that's a very exciting moment for the whole community. Some pictures have been released publicly, and they are basically the first glimpse we have of Mercury on this program. So we're very excited of getting a first taste of what we're getting at. Of course, there will be much more to come in the next years when we arrive in 2025 and in the years that will follow. But it's a big reward to get to that moment and pass it successfully. So.
Yeah, I'm super excited about this mission because it's. I was really lucky enough. Julio took me out to Kourou, and I actually saw BepiColombo being fueled up, and I also went to Darmstadt. And actually, Elsa, you were talking in front of the model that's in Darmstadt. That's the kind of technical model that you do a lot of your work on. So I feel really connected to BepiColombo. I think it's. I mean, obviously it's an amazing mission. Can you sort of give us a sort of a quick rundown of the entire mission and its purpose and how you've done this collaboration with the Japanese?
Yeah, sure. So the mission is aimed at planet Mercury, as we said, and we are privileged to go there not only with one spacecraft, but actually with two. Thanks to our collaboration with the Japanese Space Agency, we will have a European orbiter that will fly close to the planet to study things like surface and composition, exosphere, the volatiles that are there, the chemical processes that go on close to the surface. And the Japanese satellite will fly a little bit further away and will focus on the interaction with solar winds, with basically the magnetic field, the magnetosphere, and all these effects that take place a bit further away from the planet. So it's a unique chance actually to have two systems flying around the planet in parallel. That's not normally the case. You normally go one by one, but in this case we have two. So at the moment the two are flying mated with each other. They are married, let's say, and they are mounted on top of a transfer module that is taking us there. Carries chemical propulsion, electric propulsion, and two huge solar arrays to feed the electric propulsion with power. And the Japanese satellite is protected inside a structure to protect it from the sun. So we launched in October 2018 from Kourou, as you mentioned, with an Ariane 5 rocket. And
were you there?
No, I was not there. I was in the control room, ready to take over control. I never get to see the launch.
Oh,
so
we should find a mission that you're not involved with.
We see it on screen. So and the journey is very long because it's difficult to go to Mercury. It's very demanding. You cannot just go express like when we go to Mars. You just launch on a direct trajectory to Mars, and then you do a huge braking maneuver and you're there. There, the huge braking maneuver will take tons of propellant that we cannot carry. We cannot afford to carry that much. So we use instead the energy of the planets to slow us down. So we will have 9 such planetary flybys, the technique is called. We've had already 4, one by Earth and Venus last year, and then Venus and Mercury this year. And we will have 5 more Mercury flyby to gradually reduce the velocity of the craft such that in December 25 we can enter into orbit. And when we enter, we have to deliver our Japanese colleagues to their target scientific orbit and then further go down and reach our scientific orbit, and then the fun can start. The scientific fun can start. So we still have a long way to go, but still we should celebrate this milestone of this weekend. It was very important for the mission.
Yeah, I mean the orbital mechanics of these things. I mean, was that the deciding factor of sort of taking 2 spacecraft on the mission? You know, how on earth did someone sit down and go, oh, maybe we should invite the Japanese, or did the Japanese invite the Europeans? I don't know, to this kind of like vastly complicated piece of orbital dancing around the solar system.
Yeah, well, there's a bit of critical mass involved in the sense. When the mission was born, very, very early, I'm talking 2 decades ago, we were hoping to even have a surface element to this, which it was it's such a challenge to visit Mercury that, we had to drop the surface element rather rapidly, I would say. And then, it's a question that our Japanese colleagues were also looking into a program to Mercury, and then resources are knapp and the technology is difficult, and then we sat together and we decided that there would be benefit in doing it together, and that's how it ended up to be like that. Of course, it's quite a challenge on top of a challenge. I mean, going to Mercury would never have been an easy thing to do. Now, on top of that, we have a very modular satellite with multiple separations. 7 years after launch, within 3 months, we go from a stack configuration to every module going to live its own life. This adds complexity and risks to the operations, and it's undeniable, and complexity to the design. But okay, we've done all these missions, so let's do it this way. It's a quite a novel approach, I would say. Okay, we're used to stack things on other programs, no? But for interplanetary missions, it's a bit of a first, let's say, for us in ESA. All our other spacecraft so far were standalone, so it's taking us into a bit of a new domain at that level. But the science reward will be enormous. I think that must also have been a criteria in deciding this configuration. The fact of having these two systems in parallel is tremendously advantageous from a scientific point of view.
You mentioned 7 years of navigation and 9 flybys. Is Mercury one of the more complicated planets to get into orbit?
Yes, it's quite hard to get into orbit because you have to slow down too much. Otherwise, you just fly by. Basically, it's the relative velocity match that you need is it's just gigantic compared to other objects in the solar system. So it would always have been a difficult thing to do. Now it's thanks to the scientist who gave its name to our mission, Bepi Colombo, a scientist from the 20th century. He advised NASA actually on how to use combination of planetary flybys to get to visit Mercury, and it's based on his recommendation that the Mariner 10 mission in the 70s got to do its 3 historic flybys of Mercury, returning the first data we ever got from the planet close by. So we decided to honor him by naming our mission after him. But that shows it's very special from that point of view. Yes.
Elsa, could you, because it's such a complicated long journey and it takes so much slowing down to get actually accelerated to the center of the solar system, could you say a few words about the transfer module and its propulsion system? Because I know a little bit of it and I think it's rather fascinating.
Yeah, it's quite cool. Actually, I used to joke that on BepiColombo we fly almost every type of thrusters that exists because I mean for this type of missions, no? Because on the transfer module our workhorse is actually a combination of planetary flyby, which give us most of the delta V. We get 17 kilometers per second of delta velocity from the flybys themselves. It's gigantic. But in order to make that sequence, we could not rely. I mean, we didn't want to rely on just launching on the right day, because otherwise you get a launch window that basically never repeats itself. Yeah, how likely is it to get a natural combination of 9 rendezvous without doing anything in between? So actually, the electric propulsion, we use it as the glue to make those rendezvous. So it stretches a bit the trajectory there, accelerates a little bit there, so that we go from one hop to the next. And it's a very complex system. It was built by the UK. In fact, it's a British technology that was flown in that form on previous missions from wars, but not with the same performance. I mean, we had missions. Gucci mission was using this predecessor of this engine, but not with the same type of thrust levels that we use. So it was quite a challenge to assemble it and put it together. So that's one, and it consumes up to 10 kilowatts of power. That's why we have the huge solar panels that we fly.
Yes, we have a model to show the size of the solar panels.
Yes,
I think there was a rapid and scaled disassembly happening.
Okay. For comparison, the MPO consumes about 1 kilowatt. Yeah, so the power generated by the transfer module is 10 times as large. And it's just for the electric propulsion. And then we have also chemical propulsion, because we need to desaturate our reaction wheels that are used to keep the attitude. But once in a while, they have to be desaturated, and we use chemical propulsion for that. And also, when we approach planetary flybys, we need to correct the trajectory. And the electric propulsion is great, but it's not fast. I mean, you're flying the equivalent of blowing on your hand like this. It's very, very, very small. You need to fire for long to accumulate the delta V. So if you want to do a very precise maneuver, but a bit larger, and you have to do it fast, it's not good for that purpose. So we carry chemical propulsion.
I mean, when you compare it with an electrical propulsion maneuver, when you go back to the chemical propulsion, you can almost consider it as an instant change, right?
Yes, exactly. yes. So we have the two, and we switch from one to the other. Okay, we haven't had to use the chemical for maneuvering too much because our electric propulsion is very good, and the navigation has been very stable. For this flyby, we did a correction in August, and we didn't need to correct again. So it's quite, it changes a bit the operations as well. I've flown Rosetta before, and Rosetta was a purely ballistic and chemical system. And there we had to maneuver before every flyby because you accumulate errors during flight that here are taken care of by electric propulsion. So
I get the impression that you have in every historical mission.
Well, it's only two of them, but they are quite cool.
But important ones. We have some questions for the audience, if you don't mind. One of them is asking if the Japanese probe has a lander. I think it doesn't.
We've given up on landing. I mean, it's one challenge at a time. It's already it's been a long journey to get to the launch pad of this thing. And so the Japanese probe is a spinner. It's a satellite for the audience who are here. Not unlike I would say maybe the cluster satellites. It rotates around its own axis. And it has very large antenna, scientific booms, basically, to make its measurements. And it will fly on a 9 hours orbit around the planet, highly elliptical. So no landing for that one, except the crash landing at the end, of course. But that's something else.
So it will be in an orbit that will be degrading over time.
Yes.
But how long are we talking about? Tens of years or thousands of years?
Okay. I don't think we make 20 years with that one, unfortunately.
Okay.
The environment is very harsh. So the two orbits are not maintained in the sense that they will naturally decay. And there will be a re-entry, which, if I remember right, is we're talking very few years in the case of MMO. It's rather rapid, the re-entry in that case. And in the case of the MPO, we are quite lucky that, according to the analysis we've done, the orbit will be stable for about 50 years. Okay, we're coming down with a pericenter, which is from a thermal point of view, is quite demanding. So, but from an orbit stability point of view, we could keep going for a while. It's a question of how long the spacecraft will take to degrade beyond being usable. Because well, just as an anecdote, maybe the spacecraft is white. You can see it here. It's shown by the colleagues in Estec. But we know from ground tests that it won't stay white for very long because the temperature is so high that the optical properties will start degrading. And in fact, in the test, we've seen that it gets dirty brown very quickly. And then it doesn't have the same protective properties once it's degraded. Also, our solar arrays are going to be subject to this environment for which they will operate at the edge of their design to temperatures up to very close to 200 degrees. They were qualified for 200 degrees. We will have to see how long we will really survive. You know, we always say, our missions are designed for 5 years, and actually we fly them for 20. I must say Bepi is maybe one of those that won't make it 20 years. But we shall see. I mean, as long as it goes, we'll be there to make the best out of it. So we shall see.
One thing I think about Mercury is obviously its name suggests it's going really, really fast, isn't it? So once you're in orbit around Mercury, the spacecraft itself, the BepiColombo spacecraft, is going to be going really, really fast. Is there some relativistic effect that you have from flying at Mercury speed?
Well, okay, I am not the best qualified person to talk about relativistic physics, but we have an experiment that intend to basically make measurements well, I think maybe it's a big word to say to prove, but to make measurements related to the relativistic theory, because at Mercury you can. Now, again, I'm an engineer and I'm not the best qualified person to talk credibly on this, so maybe I'll pass that topic happily. For flight, we have to, I mean, our colleagues from the flight dynamics who control the trajectory of the satellite are the most accurate people that colleagues I know, and they are used to make computations a great level of detail that are required for navigating those crafts. So, for example, they do not use UTC as a time reference. They use a different time reference that takes into account the relativistic effect from flying in the solar system. No, so this I'm aware of that, but I'm not involved in the physics and the computation of that. But certainly, it's an interest. It's one of the scientific fields for this mission as well.
If I may, I have to. Logistics-wise, I think that in 3 minutes we will be sharply cut and we will all be sent to the central room. Sadly, I would continue 3 hours more on this, as usual, every time I talk to one of my colleagues, and I hope we meet again. We have one quick question. They are asking from the chat room. They are asking, Nico Caprel is asking, where is the mission control of BepiColombo?
Yeah, Nico, thanks for asking that, because of course now we are not seeing each other physically. We are actually locating in Darmstadt, Germany. It's a European Space Operations Center, Esoc of ESA. So that's in the middle of Germany, close to Frankfurt.
And I mentioned at the beginning that you are newly appointed mission manager, but up to now you were the flights operation manager for BepiColombo. What's the difference between these two jobs? What's the transition in between the two jobs? What does it mean?
Well, okay, for 14 years, since 2007, I had been fortunate to be the spacecraft operations manager indeed for Bepi. So I took it from the end of the design phase until the flight phase, basically, which meant that the job changed a lot along the years. I mean, at the beginning, it was studying paper to find out if the spacecraft would be operable and figure out what we need to do, and then make it happen and design the ground segment and validate it and get ready for launch and so on. And now it's flying it. It's implementing the mission on a daily basis, making sure that the craft remains healthy, tackle anomalies, make sure that the data comes down fine, is distributed to the users, and so on. As mission manager, it's basically functionally a bit more abstract from the direct interface to the spacecraft. It's the overall responsibility for the project. It's a bit of a project manager role. It's just not anymore dealing with the challenge of getting the spacecraft built. So in ESA, we have basically the two roles. We have the project manager that is responsible for building the spacecraft, bringing it to the launch pad together with the support teams around, and then he hands over to the mission manager at the end of the commissioning phase. So it's overseeing the implementation, but in a more managerial role, let's say. But still, there is a lot of, I think, technical coordination involved. My big responsibility as mission manager will be to make sure that we are ready to make the best of the mission and maximize sense return once we arrive on target. And I do that in collaboration with other ESA centers, so Esoc, my former group, for the spacecraft operation, and the ESA colleagues in Spain for the science operations part. I mean, Kate before and Sarah were talking about science operations as well. So it's basically encompassing more groups, let's say, coordinating across more groups than in my previous or semi-current role. I just switched 2 days ago, so it's still very new.
Yeah. And exciting, I assume. So it's time now that we have to break up. Thank you, Elsa, so much.
Thank you very much, Elsa.
Thank you, chat room. Thank you, everyone who has been watching today. We will be as well using these interviews on the main podcast. Where can people find the podcast, Matt?
They can find it on Spotify and iTunes. It's the Interplanetary podcast, or go to interplanetary.org.uk.
And I thank you, Kai, for joining us today on such short notice. Incredible help.
Thank you for inviting. And can I make a quick plug? If you want to find out more about these missions, then please visit esa.int and go to Science and Exploration. There is a web and a Bepi page. And for example, for web, you'll be able to find 3D animations in great detail of the instruments that we've been talking about, that Sarah has been describing, and of course lots of movies and information also for Bepi. So if you feel you caught a bit of iron thruster fire, then follow up.
They build what they call a structural and thermal model. This is a mechanical structure that they use to test the robustness of the structure. So they submit it to the shock, vibration, and so on of the launch. And they put on it some hardware to check out the thermal balance. So they will dress it up with thermal blankets and put some boxes that generate heat and so on. And they will make sure that the thermal design is more or less sound. So this model goes typically in a thermal vacuum chamber, like the one we have in the test center in Holland of ESA. There's a big solar simulator there. They put it there. They submit it to all the conditions that the mission will see, and they check that the design is sound. They did that for Bepi. By the way, this model is now in the London Science Museum. If you ever go to London, check it out. It must be awesome. And then they move on to this thing. So this is the electrical model. We call it also engineering model, and it's meant to check out all the data and electrical interfaces of the mission. And typically what you see, so it's the MPO is very similar dimension as a flight model. They have cut out some corners on the back side here, which is the radiator side, because they didn't need it to mount boxes, but otherwise it's the same. The structure is not the flight structure, it's a bit simplified, but the topology of the structure is identical to the flight. Because they wanted, you see, it's very crowded, and actually we're missing some boxes, so it's actually worse on the flight model, much worse, and they wanted to find out whether the harness would be long enough and so on, but they also functionally test this. This here, so the Bepi Colombo, I don't know how much you know, but it's a modular spacecraft. It's very futuristic in its shape, so it has 4 modules in total. The European Scientific Module, MPO, this is what you see here. The Japanese put also a scientific spacecraft on top. We call it MMO. It's not present here, but they have models also for that. Then we have a transfer module that is actually represented by this table here. It's in flat-sat configuration, much more complex on the real flight. That is responsible for taking us to Mercury. So it carries a chemical and ion propulsion, as well as its own power distribution and its 2 own solar panels. And then we have a thermomechanical structure to protect the MMO from solar energy during the transfer. So this you can disregard. It just looks like a nice cone on top, like a crown. It's very pretty. And they built this model here to find out the do's and don'ts of building the flight model, but also to functionally test everything. So they've used it to exercise the onboard software. It's not the only bench we have, but typically every single software function will have been exercised on this one. And we in Esoc, to test our procedures and so on, we've had a big series of tests in this as well. So when we started trying out the attitude and the orbit control modes of the satellite, which are notoriously complex generally for interplanetary, we didn't want to do the first test on the PFM, which is the flight model, which is a very precious resource. There is not necessarily much time available for that, and if it doesn't go well, you cannot retry very much. And we did it with this one. We had an equivalent of 2 or 3 weeks testing in total with this model, and Airbus is using a lot. Now, the model, the spacecraft was built under Airbus Defence and Space Leadership. So the model was initially based in Friedrichshafen for many years. Actually, our first test with it was 2012. You can imagine it was already existing for a while. The onboard computer here is that old, actually. And then a few months ago, we used a break in the campaign to move it to Esoc. And the reason was that we had the time, and now it's set up and operational here, and then we don't have to do it after launch. Everything is set up before. But still, if we have problems after the launch, we need to test out things. Airbus is fully equipped to operate it from here, and then after launch, it will transfer the control to us permanently, and then it will be basically ours. So we can exercise all configuration here. We can simulate the stack, the crew stack, where all modules are assembled together. We can simulate MPO standalone configuration. We can simulate module separations here. So play really the period where we let the MMO separate from the stack to go into its own orbit. All these operations that are highly complex can be exercised here. And to some limited extent, we can even put some hardware in the loop. So you can see here we have mechanism. We have this is an antenna pointing mechanism. There is another one on the back side. We have a transponder here as well. So if we wanted, we could do tests with radio frequency. So that could become handy. But why it's very precious, it's the electronics. It's computers, the modules we have to store data. This is very difficult to simulate to the right level of accuracy functionally. With the software simulators, we have them as well. They are quite good, but if you really want to troubleshoot low-level problems with electronics, this is an invaluable resource. So, same thing. It's a bit short. I don't know if you have specific question related to this.
Have Japan got a similar? So would we, if we were in Japan right now, would there be someone like you talking about a model of the MMO part?
I am not sure whether the Japanese have a real MMO 3D model like this one, but they have some models. We know this. They have a suitcase that can be used to check out the interface. In fact, for a while, it was located in Friedrichshafen as well. It went to Estec, the Dutch Space Center visa, before going to before the spacecraft went to the launch site. And this, you could argue that this can be sufficient. You don't necessarily, depending on what you have on the spacecraft, you don't necessarily need a fully accurate model. In fact, for the MTM, you can see we have a flat sat. It's less fancy, but it's equally effective. And in fact, for completeness, I should mention that the all-electric propulsion part, we don't have. This was actually delivered to the company with delivering the subsystem, and it's used as a test setup chain for the electric propulsion thrusters. So it's used in the live test chain for these thrusters. And if we had got it here, the room would be much more crowded because this is operating at above 10 kilowatts. So there are power supply racks like this that are monsters that generate heat like crazy, that are on high voltage, so they are hazards for humans. When they told us that, we were wondering what to do, but in the end, they needed it elsewhere, so it's good. But so you don't necessarily need the full machinery like this, depending on the complexity of the satellite. But a model where I would expect they have the onboard computer that they can run the real onboard software and maybe some electronics as well. This I would expect.
Does it add to the complexity having to deal with the Japanese? Do you have to talk to each other a lot, or are they really separate spacecraft?
They are quite separate, but we need to remember that as long as we fly together, we're one machine. So it's actually a pitfall to think of separate machines. I mean, these lessons were learned in the 60s by the Americans with the Apollo program. We're trying not to repeat that. So from the very beginning, we have established interfaces with them. But it is also true that during the cruise, they don't do very much. So we consider them a bit as a heavy payload. Yeah. So almost like, for us in our mind, it's categorized a bit as an instrument. Even so, in reality, especially in the period where we separate from them, they are two equal. They are different in size, and in weight, but in terms of contribution to the mission, they are equal partners. And in fact, it's not delivering a 100 kilos lander from a 3-ton spacecraft like it was on Rosetta. It's delivering 100-something kilo to a 1-ton satellite. The ratio is very different. Yeah? So there are aspects we need to take into consideration. We don't talk to them every day. We typically, up until recently, we had an interface meeting per year, and then we would interface per email. And we really try to establish very clear interface points, and we focus on those. So our knowledge of their satellite is actually, I would not call it very detailed. Also, we have a bend pipe interface. So basically, we do not encode their command. They encode their own commands, and then we tunnel them through our satellites to theirs. So this means we are rather blind on what they do. I mean, we have a text encoding of the pattern to have an idea which subsystem they are talking to, but we don't have the same level of control and of knowledge as we have for this one. I mean, here I can build a stack myself, but on the MMO we would not be able to do that. But it's sufficient. I mean, they are equal partners, and that's a fair way to work with, and it goes very well so far.
Fabulous. Yeah.
Any other question for this? Maybe I should mention it's not the first time we get such models in Esoc. In fact, it started with Huygens. You probably heard of this mission that landed on the moon Titan of Planet Saturn.
It was with Cassini, right?
Right, exactly. Huygens flew with Cassini, and for that, but Huygens was in ESA, the ESA component of the Cassini-Huygens mission. So it was more like Rosetta and Philae. Philae was Huygens and Rosetta was Cassini. And, but it was quite a complex surface asset, as you can imagine, landing on an unknown world. So for that reason, there was a hardware model built by industry that we got delivered to Esoc. And this played an instrumental role in testing final sequences before the landing on Titan. In fact, they even discovered some issues with this that could be then fixed. And from then, it became a bit of a lesson learned on all this type of mission, that it has a lot of value to get that. So when we started Rosetta, we discussed this also with the project and industry. Eventually, we got the Rosetta model. It's over there in that building. Yeah. Now it's being dismantled, so it's not as pretty as it used to be, because since the mission is over, we are preparing it to be hosted in a non-operational container building, so accessible to public, but not anymore used as a spacecraft for operations. So this is ongoing. And what you probably cannot fully see, but I can assure you is there. Behind there is a glass wall on that side, and you might just see that on the wall there is a sign saying Gaia AVM. So we have also the Gaia avionics model. So the Gaia is our star mapper, so the successor of Hipparcos, and basically we have a table set a bit like this one, much more bigger and more complex, that is located in the room on the back. For Solar Orbiter, we also have agreements to get the model, and for JUICE we will get one as well. So we like them. I mean, we have our own simulator as well. We have a software simulator which we use to train our teams. So at the moment for the launch, for instance, we do a Sims campaign. Maybe you heard about that. We play scenarios with a complete mission control team, contingency scenarios as well. This we don't do with this. It's very difficult to inject failures on this type of model. I mean, or you need to damage the hardware, which nobody wants. So you do it with software. But if you want to, as I said before, if you want to play very accurate scenarios down to the behavior of the electronics and timing, or debug problems with at very, very low level of the bytes being transferred from one box to the other, then you need something like this. And on Rosetta, it was used like that.
Did you have Scaparelli and things like that?
No. So for ExoMars, we didn't get a model. The ExoMars mission was developed in an extremely short time frame. They were under huge time pressure to launch. And also there, the setup is very, very complex. They have a partnership with the Russians and the Americans. And actually, the Scaparelli module, even though it belongs to the mission, it was developed, it's like the instrument, it was developed under national leadership. And when this happens, we don't typically inherit the modules. It's like what I said with the MMO. It's a Japanese module, so we don't get the module. Yep. For Rosetta, same thing. We didn't get the Philae lander here. We had test sessions with them where DLR came with a suitcase or a rack that simulated Philae. So we did interface tests prior to landing. Actually, they were very valuable, but they were always as a co-venture between two partner agencies, ESA and DLR in this case. And I think with Scaparelli it was a bit the same. And okay, there was no hardware involved. Actually, our visibility on the old Scaparelli software and testing was not, let's say, as high as we have on missions that we control fully, also from the management point of view. So this is a lesson that we keep learning, but it's difficult to put in place because the interfaces are very complex and the organization is also very complex. And the time, you need time to do this. So. And money.
Time is money.
If you don't have anything else, then I hope you enjoy your visit here. Watch this space.
Thank you very much. Thank you.
You're welcome. Thank you. Do you have any questions?
The Interplanetary podcast is alive!
But there we go. There was there was a couple of interviews with Elsa Montagnon. I'm sure I'm not saying that right, Linn, and you're not helping me. You're not going to help me here. No.
I'm not helping. I'm very intentionally keeping quiet.
I know. I've spotted.
Somewhere between the spectrum of Elsa Montagnon and maybe like Montagnon.
Yeah,
but I don't think it's the
somewhere.
latter. Elsa Monty. Elsa.
Yeah,
there you go.
Just Elsa.
I hope we're on first name basis. Just Elsa.
And obviously been on
Elsa.
this mission for absolutely ages, which is always the interesting thing about how long people stay on these missions, and you just hope they don't blow up on the launch pad or have some mysterious fault that happens to them out in space and all those kind of things. And I'm not even thinking about James Webb Telescope and all the things that can go wrong with that.
I knew you were going to say it. I was gritting my teeth. I was like, don't say James Webb, because I'm already feeling a little bit sick thinking about it, because you just said the word blow up on the launch pad, and now
it's
I'm
coming
sad.
up. It is coming up. It's being, oh my gosh, it's probably being stacked
Merry
onto
Christmas.
an Ariane 5 as we speak. And BepiColombo launched on an Ariane 5 as well. So, and that made it. That made it. That made it.
There you go. It's meant to be.
So, what are you up to this week, Linn?
This week, I am actually teaching a class because, as some of you listeners know, I do research at a university in Sweden called Uppsala University. We're actually doing a really fun first time ever course, which is joined between the sort of physics side of our university and the geocentrum side of the university. And we're talking about space resources. So it's a course, master's level course, where we talk a little bit about very sort of what if scenarios, but if you were to sort of mine on different bodies, if you wanted to extract resources in some capacity from space, how would you do that, and what would be the challenges that you face? So I'm busy doing that, writing papers, teaching, good stuff, writing emails. What about you?
I am doing a festival this week called Winter Live with my college, so I'm going to be working with lots of students, sound engineers, stage managers, creative artists, business students, all running this festival, and I've got to mark them. So it's super busy and full on, but it should be good fun. One of my students came up with a slogan for my Interplanetary podcast face masks that was "Putting your face back into public space. Which I thought was really good.
I love that. Okay, sold.
Yeah,
Get the
so
t-shirts.
I might have to start making those face masks for the next lockdown.
Oh God, no!
Just in time
whoa,
for the next lockdown. Well, what's happening? Right, right. I'm going to let the Spudcats go. Thank you very much for joining me, Linn, and let's have a Christmas special soon with everyone on.
And we can work out the orbital trajectory of reindeers from the North Pole.
Oh yes. Excellent. And if anyone knows why it's a 3-2 resonant orbit and has the definitive lowdown, let me know. Write in.
Yeah, and if anyone kept track of how many times I mentioned exoplanets, you can tally that up for a bonus thank you.
Maybe we should have exoplanet buzzword bingo.
Yeah, have a little ding 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 sound effect.
Whoever spots it first. That's it. Bye.
Bye. Bye.